to the GOCC. We're really excited to have He Guo speaking about packing nearly optimal Ramsey R3T graphs. So with that, do you want to take it away?
All right, so thanks for the introduction. Yeah, I'm He Guo, I'm from Georgia Tech. Today my topics lies in the intersection of Ramsey theory and random graph processes. And it is based on joint work with my advisor, Who's Wenki. So first, let me put things into context. Let me remind you what is the Ramsey number. So the Ramsey number is the mean number n, such that for every red and the blue edge coloring of the complete graph Kn, it contains either a red Ks or blue Kt. Well, Ramsey's theorem tells us that this definition is well defined. Because for n large enough, no matter how you color the edges of a complete graph Kn, it must contain either a red Ks or blue Kt. Understanding the behavior of Ramsey number is a major problem in combinatorics, and is well known to be hard to determine the asymptotics of such Ramsey number. A celebrated result in Ramsey theory is that the Ramsey number of R3T is T squared over log T. Well, the upper bound is due to a tie, Knosch, and Simonetti in 1980, while the lower bound is due to Kim in 1995. Nowadays, we have a better understanding of this Ramsey number due to some constant factor, and that is of work by Scherer, as well as Bowman-Kiwash, and Varese, Griffiths, Morris. But today, we focus on the order of magnitude only. Well, actually, the study of such Ramsey number R3T has been very influential in terms of proof techniques. And indeed, the upper bound by R3T is the T squared over log T. By Knosch and Simonetti from 1980 is considered to be the first serious application of so-called semi-random method. Well, for the lower bound, Elders already in 1961 found the Ramsey number R3T is at least some constant times T squared over log T squared. As you can see, there is an actual log factor between Erdős bound and the real lower bound. And this Erdős lower bound was subsequently recruited by Spencer using Loa's local lemma in 1977. And in 1974, Kirillovich used a simpler alteration method to reprove this result. And his method is nowadays called large deviation approach. And finally, it is due to K. We in 1995 managed to get a correct lower bound by removing this log factor to get this bound. And he combined a semi-random approach with concentration inequalities and differential equations. And for his major achievement, Kim also received the Boxon Prize in 1997. And the topic of the day is to introduce an extension of Kim's result, which also implies asymptotics of some other Ramsey parameters. And again, we remove some log factor. So, is there any question about the context slides of this talk? All right, so let's move on. So if we want to show a lower bound of Ramsey number R3T, the correct lower bound, what we need to do is to find an n-vertex graph G, that is, G is triangle free and with controlled independence number. Say the independence number should be at most some constant C times square root of n log n. And that is what Kim did in 1995 and Bowman did in 2008 to find the correct lower bound of the Ramsey number. Actually, to find such a low, to get such a result is not easy. For example, if we want to use a standard operation method, so it means in GNP, we try to remove one edge from each triangle to make the graph triangle free. As you can see, there is some difficulty because of the following facts. So first, we know that, by the way, the binomial random graph GNP is a random graph model, so that each edge of the complete graph GNP, of the complete graph Kn, is included independently with probability P. Here are some facts. The first fact is that the number of edges of GNP is around n squared times P. We are interested in order of magnitude. And the number of triangles is around n to 3 times P to the third. Because we try to remove one edge from each triangle to make the graph triangle free, we want the number of triangles to be less than the number of edges. Otherwise, you may cause a large independent set. And if we want the number of triangles is at most the number of edges, it implies that UP should be at most 1 over epsilon, 1 over square root of n. This is the order of magnitude of UP. But some other facts tells us if UP is such value, then the max independent set of GNP, we know that is 2 times log n over P. And if you plug such P in, you will figure out that the maximum independent set will be too large compared to our targeting bound. You can see there is some actual log factor in our targeting bound. So that's why the alteration method is an actual log factor in the lower bound. So at least we know this result is not easy to prove. Actually, in the proof of Kim and Bowman, they both use the idea of so-called triangle-free process. So the idea is simple. We just greedily add random edges that do not create a triangle. So let me tell you what is triangle-free process. The triangle-free process is that at each step, we just add one random edge so that that edge does not create a triangle. So for example, at the beginning, all the edges are available to be added. So we call them open, and we can add them one by one. So first we add this edge randomly, and next time we add another edge, this edge, and we can keep going on. We add this edge. Well, as you can see at this moment, these two edges become closed because adding them will create a triangle. So we call them closed, and we will never add them into the graph to get the G, graph G, and then we continue. So if we add this edge, then this edge becomes closed. We will never add this, those red edges to create.
So when you add an edge, is this like a uniformly random process of open edges?
Yes, that's correct. We added uniform at random. Yes, good question. So is there any other question about the process? All right, let's continue. So that is what Bowman did in his 2008 proof. He analyzed such triangle-free process to get this result. Well, much earlier, Kim used the semi-random variation of this triangle-free process. That means instead of adding just one edge at each step, he added a chunk of edges in each step. So that's the difference on this so-called semi-random approach. For our result, instead of finding just one of such nearly optimal R3T graph as Kim and Bowman did, we found an almost a packing of nearly optimal R3T graphs. That means we decompose the complete graph into edge disjoint copies of such nearly optimal R3T graph. So to be explicit, it means given any epsilon greater than 0, we find an edge collection edge disjoint graph GI in the complete graph Kn, such that each GI is the nearly optimal R3T graph. It means each GI is a vertex triangle free on this controlled independent number. So this graph behaves like the graph founded by Kim and Bowman. And secondly, the collection of such graphs satisfies that the union of the graph GI in this collection contains at least a 1 minus epsilon fraction of the edges of the complete graph Kn. So instead of finding just one nearly optimal R3T graph, you find almost a packing of such graphs. And the idea to prove our result is easy. So actually, the idea is that we start with a host graph H0 equal to the complete graph Kn. And for each Hi, we use the semi-random variation of triangle-free process to find the graph GI that is in this collection. And then we just remove this graph GI from Hi and set Hi plus 1 equal to the resulting graph. And we repeat this process. So that is, we just subsequently choose GI via semi-random variation of triangle-free process. And we have a polynomial time randomized algorithm to get our result with high probability, not just an argument of existence. So, is there any question about this, our main result?
Yeah, actually. Can you say in a little bit more detail what you mean by semi-random?
Yeah. So for triangle-free process, actually each time we add just one edge like this, and one edge at each step. But for semi-random variation, actually we not necessarily just add one edge at each step. We add many random edges at each step. So that
Okay.
Yeah.
So I mean, I guess what I'm really asking is, like, are you choosing, like, that still sounds totally random to me. So is the semi part of the semi-random just that you're choosing multiple edges all more or less uniformly at random from your current open
Yeah.
edges, or is it that you have like pre-made possible blocks of edges that you choose amongst those at random?
Yeah, so generally speaking, we just maybe we choose some edges we choose each edge with some probability, so that we choose many edges actually.
Okay, cool, thanks.
Is there any other question? All right, so let's move on. So what is the motivation? Why should we care about such problem? So first of all, if we are interested in packing problem, then you know that packing in random discrete structures has been a recent trend. And usually one packs fixed objects, such as triangles, Hamilton cycles, or matchings. Where we consider a variation where we pack objects with similar properties, since they are triangle free and with controlled independence number. Therefore, our result can be viewed as a natural packing extension of K's result. Secondly, if you are not interested in packing problem, but in random graph processes, then you know that even controlling the errors in one run of the triangle-free process is already hard. Well, we need to since we want to get such packing result, we need to control errors over lots of iterations, and that is a main technical challenge. because you need to do it carefully. Otherwise, you can imagine over so many iterations, the errors will become larger and larger, and they can take over. Thirdly, if you are not interested in random graph processing, but in Ramsey theory, then our result established a conjecture by Fox and others in Ramsey theory. We will introduce this conjecture in the next slides. All right, so here we move on to the multi-color case in Ramsey theory. So we call a graph G is R Ramsey for H. We denote by this notation G arrows H. If for any R coloring of the edges of G, it contains a monochromatic copy of H. So previously we consider R equal to 2, but here we may have multiple colors. We denote by this notation MRH to be the collection of all graph G, that is R Ramsey minimal for H, where R Ramsey minimal for H means G itself is R Ramsey for H, where any proper subgraph of G does not error H. So MRH is a collection of all the R Ramsey minimal graph for H. And actually, many problems in Ramsey theory can be understood by studying parameters related to this collection of H. So for example, if we take the minimum over all the vertices, then we recover the classical Ramsey number. And if we take a minimum over the number of edges, we also recover the well-studied set Ramsey number. Well, here we consider some other kind of parameters, that is initially studied by Berdosh and Loas in 1976. So here we are interested in, we take the minimum over the minimal degree of graph G in this collection. We denote it by SRH. Actually, for R equal to 2 case, Berdosh and Loas already found a nice result about this minimal degree parameter, and they determine this minimal degree parameter. Later on is by Fox and Lin and Sabo, Zemstan, and Zurcher. They determine S2H for many bipartite graph H. And the study of the R-color version was initiated by Fox, Grispon, Lugno, Person, and Sabo. They determine SRKK up to some logarithmic factors. We are here in this student notation. The power of the logarithmic factors may depend on K. But for K fixed and R tending to infinity, it really determine this Ramsey parameter out to some logarithmic factor. And for the special K equals 3 case, they also made some effort to optimize their Ramsey result. So for K equals 3 case, we find that SRK3 is between R squared times log K and R squared times log, or R squared times log R and R squared times log R squared. They believe their lower bound is correct. So they conjecture that SRK3 is at most R squared times log R. And we prove such conjecture. It implies that SRK3 has the order of magnitude R squared times log R. Let me mention that actually they have a nice lemma to convert the packing result like ours to a result to a bound on the SRK3. So it's enough to prove the packing result to get the bound on this Ramsey parameter. To get their lower bound, they prove the packing result by subsequently using lowest local lemma argument. So that's why there is an actual log factor in their upper bound. And to remove that log factor, they suggest to pack GI subsequently via triangle-free process. Well, for technical reasons, actually we use the semi-random variation of triangle-free process to prove our packing result. So that's in relation to the Ramsey conjecture. So, is there any question at this point? All right, now let's move on to look at our non-technical result. To prove our packing result, here is the non-technical result we need. So you can imagine that rho is some edge density parameter, and S is the size of some large vertex set. Now, if you hold the graph H in complete graph Kn, satisfies that H is not too sparse, which means for any two large disjoint vertex set of size S, the number of edges between A and B in H is at least the even fraction of them. That means the graph H is not too sparse, so the number of edges between A and B in H is at least even times S of A times S of B. If H satisfies such requirement, then we can find a triangle-free graph G in H, so that the number of edges between A and B in G is around rho fraction of the number of edges between A and B in H. And that is true for all large disjoint vertex size A and B. So you can view, so it means that the graph G is actually behave like some random like graph in H with edge density rho, but actually G is triangle free. And as you can see, G is triangle free, and since this number is greater than 1, then we know that actually the graph G has no uneven side of size 2s. So because for any two S vertex set, you can divide it into two parts so that there is at least one edge between them. So there is no large uneven side. Actually, to prove this technical result, our proof is based on semi-random variation of triangle-free process. And the benefit is that we do not require the degree or co-degree regularity of H. It means we do not require the host graph H, so that each vertex of H has almost the same degree. We do not require such regularity. This requirement, this degree and co-degree regularity is actually required by the triangle-free process. We do not need to require such regularity because we use some self-stabilization mechanism built into the process. It helps us to control the errors. As you can see, we need such result to hold for all disjoint vertex set of large size. Since there are exponential many of them, so to be the union bound, we need really good probability estimate. So some tools, probability tools, we need boundary differences inequality and some upper key of inequality of 1 key. So is there any question at this point? All right, so now let's look at how does this technical result implies our packing result. So as we have seen, we start with H0 equal to a complete graph Kn, and for each Hi, we subsequently find the Gi in Hi by using this technical result. So here, Hi plays the role of H, and Gi plays the role of G. So we find such triangle-free graph Gi is controlled independent side from H, and then we set H plus 1 equal to Hi minus Gi. And the main relation is that actually each time we remove around row fraction of edges from Hi, therefore the number of edges between A and B in Hi is around this fraction to the power of I times the number of edges between A and B in H0. Because H0 is the complete graph Kn, then we know that is at least the number of edges between A and B in Hi is around this fraction times size of A times size of B. And to apply our technical result, we just need to keep this fraction to be at least epsilon. Then we can keep using our technical result to find the Gi. And then we will stop when the number of edges between A and B is around epsilon fraction. And at that moment, since only epsilon fraction of edges are left, then by some double counting argument, you can see that the edges in Gi covers at least 1 minus epsilon fraction of the edges of the complete graph Kn. So that's how our technical result imply the technical result imply the packing result. All right, so is there any question at this point? All right, so as a summary, instead of finding just one nearly optimal R3T graph, we find almost a packing of nearly optimal R3T graph. It means if any epsilon greater than 0, we find a collection of edge disjoint graph Gi, such that each Gi is unvertex triangle-free graph on this controlled independence number. Secondly, the union of the graph Gi contains at least 1 minus epsilon fraction of edges of the complete graph Kn. And as remarks, our result is a natural packing extension of Kim's result. And we have a polynomial time algorithm to prove our result instead of just an argument of existence. And our result establishes Ramsey conjecture about SR history, conjectured by Fox and others. Let me finish with 2 questions. So the first question is actually to prove the bound on SRK3 is enough to prove a packing result that covers at least the epsilon fraction of edges of the complete graph Kn. Well, here we covers 1 minus epsilon fraction of them, which is stronger. So we are wondering, is there any other application of our K3 free packing result, or maybe Ramsey theory? The second question is that here we pack the object with triangle 3 and control independent number. So is it possible to extension to some packing result to some other kind of graph with some other properties? That is some of our work in progress. Let me stop here. Is there any other question?
First, let's thank her. I'll do the clapping. emoji. That's probably the way to do it. And we can open it up to questions.
So this is perhaps a far-flung question for He, but have you looked at all at like what this would look like on the level of matroids? So you can, for every graph, you can define some graphical matroid. Is there anything interesting that would happen if you look at your results from that perspective?
Yes. I'm not an expert in what matroid,
Okay.
but I'm not sure which kind of matroid usually.
Yeah. Yeah, maybe that's a longer question then.
If there's no more questions, we can thank her again. More clapping emojis. And I'll end the recording. Oh no, wait.